Hello all, welcome back. Last time we took a kind of high-level view of what this course is about, and we're now going to start getting into it in a little more depth. Well, almost. The first thing we need to get ourselves a little notation. Notation? Well, that's a bad word. Most people's reaction to the word notation could be something like this. So let me try to rephrase that a bit. What we'll discuss is mathematical language and communication, and notation is a part of that, and I will try to explain what it is and why it matters. And through doing that, I hope to set a basis for the mathematical foundations both of this class, but hopefully something further. And maybe change your attitude a little bit so that at least you're open to things of that form. Now, some people enjoy mathematics as just to start off with. Others find it more challenging. And one of the elements of bridging the gap is the recognition stated here that mathematics is a language, and that's the perhaps simplest way to think about it. That makes it something familiar. We are familiar with many types of languages. We use programming languages. We also use natural languages. And what makes something a language and what these have in common with mathematics is that they all have syntax, some kind of grammar and a semantics. Syntax is the symbols and sounds that the language uses. Grammar is rules about how you can put them together or not put them together meaningfully. And semantics is how you interpret those symbols as meaning. Besides introducing this, giving this as a kind of gentle introduction to notation in mathematics, pragmatically, understanding how to use mathematics and write it is going to be helpful in this class. You will do better on assessments, get more points when you can write and communicate clearly in the notation and language of mathematics. So there's many reasons to look at this. In particular, you learn to write mathematics that's grammatically correct. Not everything meshes with everything else. And beyond something that you might think of as a chore, many people think, oh my God, I understand things, but now I have to write them so that the grader gets it. You will find that having grammatically correct language and notation to support it at your disposal will enhance your ability to think clearly, not just to write clearly. So one element that's a starting point is type checking. From a programming language, you know that objects have types, so something can be of type integer or type string or so forth. Well, mathematics is no different. Strings, integers, sets, functions, algorithms are types of objects. It's a good thing to pay attention to that because when you write something, it has to be something that conforms to ways of using the types involved that are legal for those types. For example, the expression you'd written here makes no sense because you don't add numbers to sets. That's an extreme case, but you'll see that it can be more subtle than that. When you write a program, if it doesn't type check, you're going to be told. Your compiler will come back and tell you you have an error. What plays that role in mathematics? Well, to some extent, whoever is reading what you write. In this class, it could be a grader, but moving forward, it could be a reviewer of your paper or anyone receiving your work. So there is some form of checks going on, and it is good to know how to pass them. In particular, if you write code that doesn't type check, well, you won't get an executable. In the same way, if you write mathematics which doesn't type check, well, your grader can't parse it, you're not going to get too many points on your homework. So you have some incentive to do these things right. On the other hand, good writing is highly appreciated. When people write clear mathematics, their homeworks and exams are extremely easy to read and get lots of credit. A healthy attitude towards these things involves a sense of responsibility for your own writing. And some of the things we sometimes hear is people saying, well, I know what I mean, I just don't know how to say it. And maybe that's true, but the takeaway that will make you more successful is to imagine that you're graded on what you write, and nobody is there to know exactly what you meant, so you better write something that's parsable in what you meant. So, for example, this cartoon shows complaints about how people think that the problem is the other person, it's their interpretation. And when you write mathematics, you take the responsibility to do it in such a way that the interpretation is unique and the words that come out are what you meant. Okay, that may seem a little bit heavy. What does that have to do with notation? Well, notation is kind of the lowest level building block in our mathematical language. It's something it pays to get right. It pays to pay a little attention to it rather than ignore it. And when you do that, it makes thinking and writing easier. You'll find that sometimes you're struggling how to think about something or write something, and it can be resolved with a little piece of notation in a way nothing else can do. Think of notations like pawns in a chess game. From a point perspective, they're the lowest valued piece, but it's said that while they're neglected by a beginner, they're prized by the expert. So that hopefully has given you a little more motivation to actually sit through some description of basic notation. So let's go through that. And hopefully with this perspective, it's not quite as boring as it may have been before. So n denotes the set of natural numbers, that's integers 1, 2, 3 onwards. Z is the integers, both positive and negative and including 0. And z sub n, or z mod n, is the set of all integers that you can get by dividing things by n. So the remainders, which is 0 through n minus 1. We'll work over alphabets. An alphabet is a finite set of symbols, and it's supposed to be non-empty. As an example, a common one is the binary alphabet. Sigma is just the set consisting of 0 and 1. But you could look at the alphabet of English letters A through Z. You could also, from a more computer science perspective, look at ASCII. That's an alphabet in which symbols on the computer are encoded into byte codes. An alphabet describes what are the symbols, but we string those together. A string is a finite sequence of symbols. For example, Turing is a string over the English alphabet. Now, when you view it as a string, it has no semantics. My pronouncing it is completely arbitrary. From the point of view of syntax, it's the letter T followed by the letter U followed by the letter R, etc. A sequence of symbols that has length 6. Similarly, 0, 1, 0 is a string over the binary alphabet, and it has length 3. So what is the length? Of course, it's the number of symbols, and we'll denote it with bars around the string. So, as shown in the green box. Now, sometimes we're interested in the set of all possible strings. Once we've fixed an alphabet, that set is denoted by the alphabet star. Every string has a finite length. There's no such thing as an infinite length string. However, the set sigma star itself is infinite because you can have strings of any finite length. The set sigma star by definition always contains something called the empty string denoted epsilon, and by definition it has length 0. When you concatenate that with something else, you leave the other thing unchanged. Now, n with brackets around it, square brackets, is a shortening for the set of integers from 1 through n. Putting bars around something is a notation we overload a bit. We saw that if the object you put bars around is a string, you get back the length. But if it's a set, and the set is finite, then you get back the size or cardinality. So for example, if you take the set consisting of A04 and put bars around it, you get back 3 because there are 3 things in the set. This here is the symbol for the null set or the empty set, and it has size 0. Now, we will formulate problems or decision problems as subsets of strings. They will be formally the set of positive integer instances of the problem, and we call them languages. Formally, a language is just a subset of sigma star. It's a subset of the set of all strings. So for example, the set of all binary strings whose most significant bit is 1 and least significant bit is 0 is a language. Another one is this set of encodings of pairs m and x, where m is a Turing machine and x is a string and m halts on x. That would be a way of formalizing the halting problem. We saw that in the last lecture. Another problem we saw in the last lecture was reachability. We can now see that as a language. It's the set of all encoding of graphs, G, which has vertex set n and edge set e, and the graphs inside the language are those where there is a path from 1 through n. So the decision problem associated to the language that you think of when you see the language is you're given an input little x and you're asked if x belongs to the language. And so there are corresponding such problems for all the things on the right. Our quest will be to take different languages, in other words, different decision problems, and classify them according to their solvability. Are they solvable or not? With what efficiency? What type of solvability? And so forth. We will often be interested in the complement of a language. The complement is all strings that are not in the language. So here sigma star set minus L with a backslash is one way to say all the strings in sigma star that are not in L. We could also write it as sigma star minus L. Finally, we will talk of complexity classes, and these are sets of languages. So it's like going up a level in the type hierarchy. A language is a set of strings, a complexity class is a set of languages. Okay, so now turning back to the examples, you might look at the set of all valid C programs. That's a language over the ASCII alphabet. And as an example of complementation, take the first language above, and when you complement it, you get all strings, binary strings, that do not satisfy the condition stated in the first language. So you negate that condition. That means the most significant bit may be 0, or the least significant bit is a 1. Notice that the and, when you negate it, became an or. Now, notice also that technically, talking of most and least significant bits implies that there are any, and so you exclude the empty string. So the complement will have to include the empty string. Okay, so another piece of notation or type of mathematical object that we use is a function. So remember, you write functions like this, f colon and a cross product of sets, and that signifies the domain, and some other set that signifies the range. The number of sets in that list is the number of arguments to the function. There are many ways to specify a function. So you might do it in a formula. For example, the function that has domain, the set 1, 2, 4, so it has one argument, and range 0, 1, 2, can be defined in a formula as on input x, add 1 to it, mod, then take the result mod 3. You could maybe write it in pseudocode. You compute y to be x plus 1 mod 3 and return it. Or you could show a table. The table shows for every input the correct output. So f of 1 is 1, f of 2 is 0, f of 4 is 2. A two-argument function is illustrated in the next box. So the first argument is from the set 0, 1, 2, and so is the second, and the output is in the same set. The formula says that you add the two inputs mod 3 to get the result. The code writes that in a computational way, and then the table shows you for every row and column an entry which corresponds to the value of the function. One piece of notation with regard to functions is when you have a function mapping a set x to a set y, you might have a certain subset of the first set of the domain, and you want to see what happens when you apply the function to the elements of that. We thus extend the notation so that functions also apply to sets. When you do that, you get back a set, and it's the set of all results of the function applied to points in your starting set. So this lifts functions as being something applied to points to also being applied to sets. Okay, so let's exercise this a little bit. For this exercise, we'll let sigma be some alphabet. We've fixed two strings, x and y in sigma star. We've also fixed two subsets of sigma star, two languages, and some function from sigma star to sigma star. Then we will consider various expressions, and for each one we'll ask just if they make sense, in other words, if they type check. Now notice that usually if you're given an expression, you might think you're asked to determine whether it's true or false. But that's not what we're asking here. We're asking whether it makes grammatical sense. And in fact, I haven't even given you enough information to know if it's true or false. But the question of whether it's true or false can only be meaningful once it makes grammatical sense. So that's the first thing to look at. So for example, the first thing says x1 is a subset of A. Well, that doesn't make sense. Why? Because it doesn't type check. Subset is a relation between sets, but the thing on the left is not a set, it's a string. A little typo there, I see. I should be writing x in place of x1 everywhere. Similarly, consider x1 not a member of A. Does that make this sense? Yes, because x1 is a string, and so you can talk about it being a member of the set A or not, because A is a subset of strings. Of course, I don't know whether it really is or isn't. There's no information given for that, but it's a question one can pose. You could also write, consider the singleton set consisting of x1. Is that an element of A? That does not make sense because the elements of A are strings and the thing on the left is a set and it doesn't type check. You could write whether uppercase A is an element of uppercase B. It doesn't type check because the elements of B are strings and A is not a string, it's a set. You could put braces around the singleton string, the string x1 to create the singleton set and ask if that's a subset of A. That makes sense because on the left and right you have sets of strings. And it's the same thing as asking if x1 is a member of A. Of course, A and B being sets, you can ask if A is a subset of B. You can ask if f of x is a subset of A. That does not make sense because f of x is a string, and a string is not a subset of A. It could be a member of A. But if you apply f to A as a set, you get back another set. And there you can ask if it's contained in A. Okay. So in this way, whenever you write things, try to make sure they make sense. Furthermore, as we go through the class, you'll meet all kinds of new mathematical objects, Turing machines, complexity classes, reductions, and so forth. One way to understand them mathematically is whenever you meet them, you ask, what type are you? And once you understand that, it'll much improve your ability to work with and manipulate these objects. Okay, let's stop there.